In this series of videos, we're going to ask an obvious question that arises when we track the trajectories of two objects in the same space. And in particular, we're going to look at whether those objects would collide if they follow those trajectories, or possibly a near miss or a far miss, where they go through the same point in space, but at different times. And there's obvious tie-ins here to important engineering safety things, such as autonomous cars, as well as tracking spaceships, space debris, and ensuring that there wouldn't be collisions between known objects when we're in outer space as well. We're going to look at the mathematics of this and see how we can test strategies using our ideas about trajectories and them being formulated as vector-valued curves. So we're going to start with this example where we have t squared and t and a separate trajectory called u with 3 minus 2t and 4t minus 3. And we already have hopefully a bit of intuition. This looks like it's going to have some kind of quadratic shape based on the relationship between the x and y coordinates, and the fact that the x and y functions here are both linear in t would lend us to believe that this is going to be a straight line somehow in xy space. But let's just do a quick review of this with our subbing in values, a table of values. Start with t, and this is going to be for r of t. And we'll do our usual span here. There's no domain issues, so we'll start negative, go positive using nice integers. Negative 2 squared for x is 4. Negative 1 squared is 1. 0 squared is 0. And 2 squared, 4. And the y values are even easier. They are just the same numbers as the time values, same as this column here. So we can see fairly quickly here, do our quick sketch of the axes. If we draw the u curve, then it's going to track 4 and negative 2, 1 and negative 1, and like so. That will be the curve traced out, and if we check the direction as time is increasing, we can add some arrows on that, and that would define the r of t trajectory. So a particle moves along here, time 0 it reaches this vertex and then keeps going. On the other hand, the second trajectory is going to be u, and it has t and x and y coordinates as well. For consistency, let's see what we get here. And 3 minus 2t, 3 minus 2 minus 4 is going to give us 7 for x. And let's just keep going through the x's first. 3 minus 2 plus 2 rather is going to be 5. 3 minus 0 is 3. 3 minus 2 is 1. 2 minus 3 minus 4 is going to be negative 1. So we see our x coordinates start at 7 and then work their way back towards negative 1 here. In the y direction, what do we have? We have 4 times this, that's negative 2 times 4 is negative 8, minus another 3 is negative 11, and each time we go up 1 in t, we're going to go up 4 in y. So negative 7, 0, just to double check, is minus 3, 1, everything's positive now, it's a little easier, it's plus 1. And last but not least for this table is 8 minus 3 is 5. And yes, indeed, we see this is going up by 4 each time. That's nice. Just clean up that 1 a little bit. And that gives us a little harder to see here because we go off the axis pretty quickly, but we have some points that we can refer to, such as, let's do this in black, 1, 2, 3, 1, 2, 3, 3, negative 3, and then 1 for x and 1 for, oh, there's a possibility right there, and negative 1 and 5. 1, 2, 3, 4, 5. Here we go. So we should be able to draw a straight line through those, and so-ish like that. And that trajectory, the x's are decreasing as time goes up. If t goes up, we subtract more, and so the x decreases, and that gives us a relationship or the direction of travel being up and to the left here. And without any actual calculation so far, what we see is that there will be at least 2 intersections. We don't know the timings of this, but we know that this blue line is going to pass through this coordinate and this coordinate, as too will the black line defining the u trajectory. It's now our job to figure out how can we use some mathematics and the algebra to identify those 2 points and determine whether they are collision or just a missed intersection where one particle goes first and then the second particle follows to that same point a little later. Well, what do we mean by collision? If we imagine our axes here and we take two patterns and let's just keep them essentially random for this time so we don't confuse ourselves with the real graph that we're looking at in this example, we would have a collision if we are at the same xy point, but that's not enough. If we're at the same xy point, but at the same time. So in other words, we can be coming from below here, but we have to reach that point, say at t equals a, and then we have to be going along the blue line and reaching the same point at t equals a, same point in space, same time. That's what we mean by two particles colliding. That's how you'd run into someone on the stairs, is if you're both in the same location at the same time. Contrast that with the idea of trajectories that just cross or that intersect. We still need the same location, so we're going to have the same xy point on both trajectories, but different times. And we're going to explore how to represent that. This tends to be the slightly more confusing one. This one, most of us can kind of get our heads around pretty quickly. So imagine here, if we're going along this curve and we reach this coordinate on the black trajectory at t equals a, but as we come along the blue line, we reach that same point, but at t equals b. Or what we're going to do is call this maybe t1 and t2. That makes it nice and clear. We're going to actually change that as another thing that makes sort of sense. We might use t for one of these and a variable very close to t that's still going to play the role of a time. You'll see frequently s being used for these kinds of problems. And the idea being there's some number for time on this trajectory and some number t for time on this trajectory that both lead to the same xy coordinates. So a quick setup of the equations. What we're going to have here is the x on the r curve is going to equal the x on the u curve at the same time. So we're going to be able to use t for both these equations. If there's a t, I can sub into the x coordinate for both of these and get the same x. That's halfway to a collision. The other part, of course, is that our y coordinates would also have to match. And it's just really easy to sort of mix and match these accidentally, but we want the x coordinates to be the same on the different paths. So it's going to be these two things here have to equal each other. And then the y coordinates have to be equal to each other as well to have a collision, and at the same t. So all of these have to work together. The difference here for intersection but not collision is that the x on the r value, or the r trajectory, has to equal x on the u trajectory, but possibly different times. At, let's phrase it this way, at the x time, sorry, not the x time, each trajectory is separate. That's where it's easy to get confused. The r time equals t, and the u time equals s. So that's where we're going along. Say the black line here is our r curve. When we get to this point here, we're going to call that time t. Meanwhile, on the u path, we're going to cross it along, and we're going to say time is being called s on that curve, and we're going to reach it at some special time s. So the other equivalent thing is if we also need the y coordinates to be equal. So the y on the r has to equal the y on our u curve, and again, possibly at two different times for r and u. We'll see how this plays out in the math. That'll hopefully make things more concrete. We're going to start with the collisions because, as again, I mentioned, that's usually what people see as more straightforward. Let's see how that plays out here. So the x coordinates have to be equal at the same time. So the x coordinates for the two trajectories have to be the same. That means t squared has to equal 3 minus 2t. And we need, for the y coordinates to be equal, we have to have t equals 4t minus 3. And so how do we play these two things together? Well, it's just two equations and one unknown. So in fact, we can solve this a number of different ways. If we look at equation 2, simply because it's all linear, that's the tempting one to start with. From it, we can learn that if we bring the t over here, we'll have 3t's. Bring the negative 3 over here, we'll have 3. And we're going to get t equals 1 is the only solution. So the y coordinates were going to equal each other only at t equals 1. Now the second follow-up is whether that time also gives us the same x coordinate. Maybe we are at the same time in the same y, but different x's. Let's see that. So we're going to check if the x's are equal at t equals 1. So we're not subbing in, we're just checking to see whether that's true. The left-hand side of equation 1 is going to be t squared, which is equal to 1 squared, which is 1. The right-hand side of equation 2 is 3 minus 2t. And when we sub in our 1, that's going to be 3 minus 2 times 1. And that is 1. Excellent. So we do, in fact, see the same x-coordinate at t equals 1. All that together does point to a collision. So at t equals 1, the particles collide at, we already found it, the x-coordinates are both 1, and the y-coordinates, actually we didn't check that in, but the y we can get by quickly subbing in back into equation 2, and we're going to have 1, 1 as our intersection point. Going back to our diagram for a moment, our sketch, that would be this intersection point that we saw earlier, only now we know it's more than just an intersection, it's actually a collision. At time 1, both particles are in that location. The fact that this other point didn't show up in our analysis, though, says there's going to be a second intersection and it will not be a collision. It must be two different times that we're passing through this. Otherwise, this equation solving would have turned up that secondary point. So how do we find the location of that intersection as a follow-up? Well, remember, we're going to look at x, and we're going to have our r of t here, and it's going to be equal to u. I can't use t because that would mean we're tracking both trajectories at the same time, the same passage of time. We're interested in the same location, different times. And if it helps, I like the t and s version. Let's just move this down a bit, give us some space so you can write it different ways if you like. Another way to think about this would be r at some time 1 is equal to u, the xy coordinates of u, at some time t2. The reason I don't use this is simply there's too many subscripts, and by the time you have subscripts and squares, it's a lot of bookkeeping. T and S look different, they're easier to write. It's entirely a style choice. I would argue that this probably carries the meaning more clearly. This is just easier to work with when you have multiple equations you're trying to solve. So let's set up those equations. So we're going to align these vertically. For the x-coordinates, we have to have t squared equals, this time it's u at some not t, but some time value s. So our second time, and that'll be 3 minus 2s. And our y-coordinates are the same equalities here, but let's do that in the same color we did before, just for consistency. It's t on the left-hand side, but anything to do with u, we're going to use the time value s for s minus 3. All right, and that gives us our two equations again, only now we have a little more freedom because we have two variables that we can track down. Looking at this, it's probably easiest to take s and put it into this equation so we don't have some nasty things to square. And if we do that, we just solve for s here. We're going to get t plus 3 equals 4s, or s equals t plus 3 all over 4. Let's call that equation 3. Equation 3, we can now sub into equation 1 and see if we can track this down. So right now it looks like we can get the y-coordinates to align as long as the t's and s's have a certain relationship. But now we want the y-coordinates to be, the x-coordinates to be equal as well. How do we achieve that with this constraint? Well, we sub 3 into 1, and we get t squared equals 3 minus 2 s's, but each s has to equal t plus 3 over 4. There we go. And we're just going to tidy that up a little bit. We're going to get t squared equals 3 minus 2t over 4 is t over 2. And 6 over 4 is 3 halves. No one likes solving quadratics like this, so we're going to put that into equals 0 form. So we're going to have t squared plus t over 2. And by the time this is done, it's positive 3 over 2. When we bring it to the other side, it's negative 3 over 2. So simply manipulating this equation and looking at these two things here, which are equal to positive 3 halves. When we combine them, we bring them over to the other side, they become negative 3 halves. And that is not super obvious to factor, but that's going to be t something and t something equals 0. And what something's product of minus 3 halves, sum of positive 1 half. That sounds like 3 halves and 1, and let's get the signs right here. There we go. We'll have minus 1 plus 3 halves. That'll be plus t over 2 for the middle term, and negative 3 halves there. Factor however you like. Use the quadratic equation if that floats your boat. It doesn't really matter. The key thing is you're going to arrive at two possibilities, t equals 1 and t equals negative 3 halves. So what's that telling us? It's telling us that the intersection times on R, where we're going to go through the same point as the U-curve. And so we see 2 times. And that makes sense because we go back to our diagram, we were expecting to find 2 different times. If we're following the parabola on R here, we would encounter this point here at negative 3 halves time, negative 3 halves seconds. We keep going, time 0, and then time 1 gets us here. Oh, we already knew about that point. That's our collision. But now we can focus in on this intersection point more clearly. It'll be at this time, negative 3 halves. We're going to go through the full process here, though, and just remind ourselves of how we would get all the other information that we need. In particular, if we have s equals, let's go back here, we had s equals t plus 3 over 4. So at t equals 1, our s value, which is what time are we at in the u trajectory clock, we're going to be at 1 plus 3 over 4, much better known as 1. That was our collision from earlier. And that was at the point 1, 1. And the new point, the t equals negative 3 halves, our s, again using our equation 3 here, our s is going to be negative 3 halves in brackets plus a big 3 all over 4. And that's going to take some algebra. Grab your calculator with the fraction tool if you like, or work it out longhand, negative 3/8 plus 3/4. And, oh, that's half of that. We're subtracting it. That'll give us positive 3/8 when we're done. And so we have the time of that second intersection. Now let's just confirm the same xy for both trajectories. How do I know for sure that we haven't made a mistake? Well, at t equals negative 3 halves, r of negative 3 halves is, using the formula up here, is t squared, so positive 9/4 rather, because we're squaring, and t itself is negative 3 halves. And meanwhile, the value we found for the u curve, which is s, is 3/8. U at 3/8 is 3 minus 2 times 3/8. And let's do the other one while we're here. 4 times 3/8 minus 3. And again, if we do our quick calculations, that's minus 3/4. Oh, that's exactly 9/4. Phew. And also, if we do the algebra here, this will be 3 halves minus 3. That's also negative 3 halves. And so we have an intersection at 9/4, negative 3 halves, And so we can actually add that to our diagram here, way back at the beginning. This location is exactly negative 9/4 rather positive, and -3/2 in the y direction. And we also know exactly when we're going through those 2 points. So focus initially, if this is new especially, on the rationale for why we set the x and y equal, but use different time values on either side of this equation. One time value for one trajectory and a separate distinct time value for the other trajectory. And just because it helps to confirm these things, there's some code here that you can look at. We're simply going to run it, but we'll see an animation of both those trajectories, and we'll see the intersections at, keep an eye on the times. 3/8 was the straight line trajectory, and time -3/2 was when the parabola went through that second intersection point. And then at time 1, they both also collided. So we're going to animate that here and see what that looks like. So we have the arcs here, and as the timer moves forward, a little haltingly, we see that the trajectory on the parabola is going to reach this point earlier at well, let's wait for it. Oh, look, -3/2 or -1.5. Then we're going to have to wait until time goes past 0. 0 is when this arc actually reaches the vertex. And we should see the black dot hit this intersection point at 3/8, which is around 0.4, 0.37. Perfect. And then as we get closer and closer here, we see the full collision at time equals 1. So a quick diagram tells us that there are 2 intersections, period. Doing the careful analysis of the algebra lets us determine which of those intersections, rather, are actually collisions or just passing through the same point at different times, and specifically where and when those